title is Why Strings? Because I think very often people have heard about string theory a little bit, and then they ask also, okay, string means like, okay, we all know what ordinary strings are, one-dimensional rubber bands or kind of a piece of thread. They're all strings, but why are people thinking about string-like objects like that? And one of my goals in this talk is to try to convince you that it's a very old idea in some sense and a very natural idea. And string theory is a very natural part of the framework of describing nature. And even amongst the things that we know well, and that it has therefore given us a foothold in trying to understand things that we don't know well. And so I will try to tell a bit about how some of that understanding has come. But I'm assuming that many of you are all bachelor students and may not have some specialized kind of knowledge. So I'll start from the very beginning with fundamental interactions. So it is quite remarkable that we have various different forces in nature, and they are all manifestations of four fundamental ones, namely the gravitational force, which all of you feel, we all feel when we are here on Earth itself, or anywhere in the universe. Gravity is always there. And it was the oldest force, but there is also the electromagnetic force, which we have learned about, and which you have all studied also in your courses, and I will come back to these things. But maybe less familiar are the other interactions which operate at much smaller length scales, such as the strong interaction, which operates inside a nucleus, which is sometimes called the theory of the strong interactions, is called quantum chromodynamics. I will say more about that also. And finally, there is the weak interactions which govern radioactivity, once again in the nuclear level. But this is something which we now understand is intimately tied with the electromagnetic force. But in any case, these are sort of the four conventional fundamental forces of nature. And there is a fascinating story for each of these forces about how we deciphered the nature of these forces, how we also understood their different manifestations. And this is, of course, an still unraveling story, because even with the electromagnetic forces, we still don't understand the many different phases of matter that can be formed. So it's still a very ongoing story to understand how the many ways in which these forces can appear in nature. So one of the themes in my talk will be that strings naturally arise in these descriptions, in trying to understand deeper some of these interactions. Strings naturally appear. It is not just something you have to necessarily dream up. So let me try to do that a little slowly. Let us talk about the first force in that list, gravity. Gravity is, of course, the most apparent force in nature. We all feel it. Newton. And it is also the first force that we managed to have a complete, not a complete, I should say, have a good universal understanding of, because this is what Newton famously proposed as the inverse square law force, which all of you have studied in high school and undergraduate physics, about the force between two gravitational bodies is proportional to the product of their masses and inversely proportional to the separation R. And this was universal in the sense that it describes gravity on the Earth as well as in the solar system very accurately. And this was the triumph of Newton's law, that it could predict many things about the planetary orbits. And we use it even now whenever the space agency sends out satellites or rockets, we are always using Newton's laws. But what we have learned now since Newton's time is that when we go beyond our solar system, and even in our solar system, there are some small hints. But when we go beyond the solar system, we realize that there are much more extreme circumstances where Newton's law is only approximately true. And we have to have a more complete description. This is how it often is in physics, that you have a law which is very good, very successful, but it has a domain of applicability. It has a regime where you can trust it, where it gives accurate answers. But there is some, when you go beyond that regime, or that domain, you see that it must be incomplete, and you need a larger, more general law. And this is what Einstein did. He realized that Newton's law was inadequate under some circumstances. For instance, when the velocities of objects are close to the speed of light, or actually even when the density of objects are very strong, then Newton's law is not actually a good description of the force of gravity. And indeed, he had an alternative view description of gravity. In terms of the geometry of space and time. And so he realized that the gravity is in some ways encoded in the curved space geometry of space-time. And this is the theory of general relativity. So I won't, of course, be able to explain all this to you in detail, but you may have heard these statements that somehow the curved geometry is what is a way of capturing the effect of a massive body, or a body which has energy. So in some sense, gravity is entirely geometric. So this was Einstein's wonderful insight. And I will leave you at this stage with that description of gravity. We will come back to this later, about how even this Einstein's description of gravity is inadequate, and we need to go beyond that as well. But that we'll come back to that. Let's look at the second force on our list, electromagnetism. This is the interaction which is responsible for most of the complex arrangements we see around us, of liquids, solids, gases, and their interactions, their different phases, many unusual properties of materials. Some are conductors of heat and electricity, others have other properties of being malleable and whatnot. So the chemical properties, physical properties, a lot of them arise from electromagnetism, because ultimately in a solid or a liquid, the particles are they are built out of atoms, and the atoms are essentially interacting with each other electromagnetically. But before, that is jumping ahead of the story. When the electric and magnetic forces were first understood, either in the context of electrostatics or in the context of magnets, they seemed like very different forces. And it was quite an important achievement to unify these electric and magnetic forces. And this was what the ideas of Faraday and Maxwell brought about. And this culminated in Maxwell's equations, which we have all studied. And one of the big triumphs of Maxwell's equations is that it also, in addition to describing electric and magnetic forces, also managed to show that light can be understood as an electromagnetic wave, which can be created by accelerated charges. And this was experimentally also tested. And it was quite an important achievement in the 19th century, that people realized that light, electricity, magnetism, these are all just different aspects of this force of electromagnetism. But I want to dwell a little more on this, because this will be important for our theme of strings, because if you actually study a bit about the history of how the classical electromagnetism was obtained, there were actually two pictures. One you can say is a Maxwell picture, and another is a Faraday picture, at least as a very crude way of describing it. So what are these pictures? You have all studied them. Faraday tried to think, and this is the right-hand side of the slide, Faraday tried to think of electric forces or magnetic forces in terms of these flux, lines of flux, which you have probably even from school been exposed to. In fact, that is how usually electricity and magnetism is initially introduced. When you have a magnet, then you have some lines of force around it, which you can actually see, visualize by just sprinkling some iron filings. You can actually see these lines of force, or you can put some compasses and they will all point in the direction of these lines of force. So this was Faraday's picture, and he applied it to both electricity. So you can have a positive and a negative charge. That's actually the case I've kind of shown over here. Say an electron and a positron, a plus charge and a minus charge. The lines of force or flux will look like this. But the picture we actually use when we describe electricity and magnetism, what you have studied in your undergraduate electromagnetism course, is in terms not about these lines of force, right? I mean, you have studied in terms of electric fields and magnetic fields. So these are fields, these are like vectors, and a vector corresponding to the electric field, another vector corresponding to the magnetic field, and each of these vectors, it's a field because it depends on the position and the time. The electric field might be time varying, the magnetic field may be time varying, and you write down these differential equations which relate the time varying of these fields to their spatial variation, and that is how Maxwell's equations are formulated. So it's a very different picture. This field picture is very different from this side. The left-hand side seems quite different from the right-hand side, these lines of flux. But there are two equally valid pictures with which to view classical electromagnetism. So one is localized, these point-like fields. The other is extended. That's, in a sense, the difference. This is a localized description, just point-like fields. This is in terms of these lines of flux, which are therefore spread out and extended. So though I have presented this as some kind of Maxwell versus Faraday, actually it was historically not quite like that. In fact, Maxwell was very influenced by Faraday's picture of the lines of flux, and he tried to write down equations first. When he tried to write down the equations for electricity and magnetism, he actually tried to write down equations for these lines of force or these lines of flux by modeling them as some kind of small narrow tubes. And in that time, the people had the intuition of fluid flow. So he tried to think of this as some kind of a flow of some kind of fluid, and tried to write down equations for that fluid. But he was not successful. These equations were very clumsy. He was not able to write down any good set of a good mathematically precise description of these lines of force. So ultimately, he hit upon the idea that it is not the lines that it's easy to write equations in terms of. It's easiest to write equations for these vector fields, the ones we had also on the previous slide. And so then he wrote down these equations, which you have all seen, I suppose. After Newton's law of gravity, this was the first major advance in understanding of fundamental force, these Maxwell's equations, which, as you can see, nicely combine the electric and magnetic fields with each other. And as I say, the rest is modernity, because our modern civilization is essentially grounded in these equations. Everything, these electric, all our electric motors and dynamos and all the gadgets that we use ultimately rely on electric and magnetic fields. and of course the light, the phenomenon of light that I mentioned, and all the things about optics. Okay, so I talked about two forces which were understood already by the 1900s, namely the gravity and electromagnetism. But there was a new realization that came in the early 20th century, which is that ultimately matter seemed to be made out of atoms. And Rutherford famously discovered that atoms consist of a positively charged nucleus with negatively charged electrons moving around it. And most of the atom is, in some sense, empty space. The nucleus is very small and concentrated at the center of a larger atom, and the electrons are almost point-like, and they seem to just be moving around this nucleus by electromagnetic interaction. But this posed a major challenge to physicists, because Maxwell's theory, and I just mentioned this, that tells you that when a charged particle accelerates, it will radiate, and that's how light is generated. And that's how in a dipole oscillator you generate light. So you would think that these electrons which are moving around and orbits in around the nucleus, they are accelerating. You know that objects which are moving in a circle are accelerating. So why don't they radiate, and why don't they then lose energy? And when they lose energy, they will kind of spiral into the nucleus. So why doesn't that happen? How can you have stable atoms? So this was a big puzzle. At the same time, another puzzle arose with respect to light. Light itself, people thought after Maxwell, it's a wave-like object, and it exhibits wave-like properties. So it is an electromagnetic wave. We understand nothing more to it. But then experiments like the photoelectric effect showed that light also has a particle-like nature, and that was called a photon. So it was very puzzling how it could simultaneously be a wave and a particle. And this was, in fact, this is a cartoon that I found on the internet, which I think says it very well. If you read it over here, you can see light is if you see it in one way, it says WAVE. But if you see it another way, there is a PARTICLE, right? I hope all of you see this. So you can either see the writing as a particle, or you can see it written as a wave. So in a way, this nice cleverly captures the same aspect that same aspect of this wave particle duality that was first seen for light, that either you can think of it, in some experiments it shows a wave-like nature, in some it shows a particle-like nature, and it seems to be simultaneously both. So this was very puzzling, and did not fit into, again, Maxwell's description or anything. And so people had these puzzles, and finally this was reconciled also by the quantum theory, which in fact also said that not just light, but even what we think of as particles like electrons or protons or any other particle-like object also has a wave-like nature at the quantum level. And this is, of course, the de Broglie hypothesis, etc. But the machinery of quantum mechanics, the theory of quantum mechanics, was developed about a century ago, and naturally built in this duality, this wave-particle duality that is built into the framework of quantum mechanics when we describe it in terms of a wave function, etc. So quantum reality is sort of gave yet another, gave a new way to think of that we need to re-examine our classical notions, even in electromagnetism, if we have to reconcile it with the quantum theory, which seems to be the underlying description, and the classical description as only an approximation. So this was what in the last century people have further developed. And the culmination of quantum mechanics was this framework called quantum field theory, which in some ways is the quantum generalization of the classical field theories of, say, Maxwell and etc. This is a comprehensive framework. It unifies the wave-particle duality because you have a quantum field. You can think of it, it has wave-like excitations, but it also has particle-like excitations, localized excitations, and you can have a mixture of both of them. In some sense, all excitations are, you can have a dual nature of both wave and particle-like. This is a movie about these fields at the quantum level. There are also these so-called quantum fluctuations because of the uncertainty principle. And this is a movie of which is based on numerical simulations of the actual fluctuations in a vacuum even. And you can see that there are all kinds of oscillations or excitations. Ones which are localized you can think of as roughly particles. I don't have any excitations here which are wave-like, but if you gave it some energy, there would be a wave-like excitation which would correspond to a usual plane wave of electromagnetism or whatever field. So this framework of quantum field theory was first developed to apply to electromagnetism together with the matter like electrons or protons, etc., that would interact with which would interact electromagnetically. And this theory, this quantum field theory of electromagnetism, was called quantum electrodynamics, or QED. And it is a very successful theory. It describes very accurately how electrons interact with light. And I like to emphasize to an audience like yours that this is really a triumph of the scientific method. So if you want to see what is the real power of the scientific method, it is in something like this. You see, these are two numbers I have written over here. They are related to the so-called magnetic moment of the electron. But never mind the exact definition. You can compute the magnetic moment of the electron deviates from its classical value, and this deviation is what is actually represented here through this number A. The theory, the QED, the theory of QED predicts, if you develop to high enough precision the theory, it predicts this number on top. And you can see experiments, amazingly, can also measure to an accuracy of something like 10, 12 decimal places. And the two are matching up to the error. So there's an error over here. These terms in the bracket correspond to the error. There's a theoretical error because you only calculate up to a certain order. There's an experimental error, of course, in the measurement. But up to this error, which is in just the last 3 digits here and the last 2 digits here, you see they agree with each other. The agreement is remarkably successful. I think in no other discipline of science do you have such agreement up to this decimal place, you can see. And people will only refine this further. So it's a triumph of both the experiments and the theory and their remarkable matching. So this is why quantum field theory is a framework which is very well established. There are many other things that have been computed and matched with experiment in this theory, which tell you the corrections to Maxwell's equations coming from quantum effects. And it matches beautifully. So this framework of quantum field theory is very powerful. So you can ask, why was this very successful? How could you actually compare the theory and the experiment to such high accuracy? So one of the reasons for this success was that the strength of the interaction, or what is called the coupling between the interaction strength between the charged particles, is governed by a dimensionless quantity, which you can think of as built from the fundamental electric charge of the electron divided by this Planck's constant and the speed of light in the appropriate units. This is a dimensionless quantity, which is approximately 1 over 137. It's a pure number, 0.01, it's less than 0.01. So and this measures the strength of the interactions between two electrons. And you can see that, like Coulomb's law, it's proportional to the product of the electric charges. So this is the fundamental strength that governs the electromagnetic interaction. And because this is very small, it is this number which governs the size of the quantum effects. This is sometimes called the fine structure constant. So this fine structure constant in electromagnetism is very small, it's less than 0.01, and therefore the quantum effects are actually quite small. And the classical description in terms of electric and magnetic fields is a good first approximation, where you can kind of neglect this term, terms which are of this order. So this is why Maxwell's equations are so successful. And this is why if you're an electrical engineer, you don't need to study quantum electrodynamics to design a motor or an electric bulb or the circuits in your house. You just need Maxwell's equations and those that follow from that for our electric currents and so on, which is all classical. So that description is good enough. Quantum effects rarely play a role in our everyday experience with electromagnetism. And this is the reason. That's what I want you to take away. That the reason is that this number is very small. That's why we don't have to worry about quantum effects when we describe electromagnetism. But at the same time, one thing I should emphasize, because of what I said earlier about this Maxwell's fields as well as the lines of flux. So actually, in hindsight, one can understand why Maxwell's attempts to describe in terms of these lines of force or lines of flux was doomed, because these lines of flux, as I showed you in those drawings earlier, they're actually very big. I mean, they are spread out all over space. When you drop these ion filings, or when you draw the lines of force between a positive and negative charge, you draw these lines going all the way around, right? The electromagnetism is a long range force. And so these lines of force extend all the way. So they are not very rigid objects. They're very floppy objects in that sense. And that's one of the reasons in hindsight that it's their dynamics to write equations for those lines of flux was very difficult, because they're not really rigid. When you have a rigid body, you can write more easily its equations of motion as compared to something which is just completely non-rigid. So, okay, so that was, I told you about the quantum effects of quantum aspects of electromagnetism. But then as people probed further, the 20th century brought out these new force, this strong interaction, because the nucleus that we described, the Rutherford found, this nucleus is built of positive charges, is made of protons and also neutrons, but neutrons carry no electric charge. But the protons all carry the same positive charge. And so if they are to hold together in a nucleus, you need a new force which overcomes the repulsion between the protons, the electromagnetic repulsion, and overcomes that by a stronger force. So that's why it's called a strong interaction. And now we understand that these strong interactions really operate at the level of quarks, which make up the protons and neutrons. And this force is much stronger than electromagnetism. And in fact, this force is very unusual. It is very different qualitatively from electromagnetism, in that the force grows with the separation and it confines the quarks. it doesn't allow the quarks to go far away from each other because the force grows as you try to separate the quarks from each other. So very much unlike in electromagnetism, where as you separate two electrons or electron and a proton, the force decreases. So it decreases with separation, whereas here it increases. And actually, if you think of it in terms of the lines of flux that we had for Faraday, there's a similar mechanism operating here, but there is an important difference. The lines of flux are not spread out all over the space. So think of this as a quark and this as an antiquark. The lines of flux, very similar to the Maxwell's lines of flux, that there are similar lines of flux for the strong interaction, but those are now bundled up into a string-like tube which extends between the quark and the antiquark. I mean, like between two of these charged objects under the strong interactions. And this is actually a sort of again a movie of a simulation which shows that if you try to separate a quark and an antiquark or two such strongly interacting objects, the lines of flux are actually all concentrated in the region between them. You can see that is what I had tried to draw over here. And you can see it's like a thick object. It's like a thick string-like object. And this represents the energy density. So all of the flux is essentially the flux outside this tube is almost zero. Most of the lines of flux are in this tube over here. It's a string-like tube. So that's where the first time I'm introducing this word string, and we'll see that is not a coincidence. But people had not thought of it in that way initially. They tried to describe the strong interactions in a way generalizing that of Maxwell's theory. And indeed, there is a beautiful generalization of Maxwell's theory called Yang-Mills theory. It is a quantum field theory. And this theory was developed, and just in analogy with quantum electrodynamics, it was called quantum chromodynamics because of the underlying color force that this was kind of charged. These were just a term. It has nothing to do with actual color. It's just a term, and this quantum chromodynamics was the term that was invented, or QCD as it is called. And there is a description in terms of this quantum field theory of QCD. But there was this string-like picture that seemed to be also underlying it. Those of you who know condensed matter physics may have heard of this thing called the Meissner effect, which is there in superconductors, that when you try to put a magnetic field, the superconductor tries to push out the magnetic field. And the magnetic field cannot penetrate it usually until you reach a certain critical value of the magnetic field. Then it starts penetrating, but even then it won't penetrate the superconductor like in a normal, it's not spread out over the superconductor. It is actually in a thin tube. And so so if you wish, this behavior is something you can see in electromagnetism also, the idea that all the flux is inside a tube. You can see it, but in conditions like those of a superconductor. You don't see it in the vacuum or in empty space or in the weakly interacting media. So here I want to just pause and share a quotation of Paul Dirac, one of the famous physicists of the 20th century. And in 1956 itself, he was trying to picture, actually he was trying to just study electromagnetism, and he was trying to make the picture of Faraday more precise. And he was saying that maybe you should revisit the Faraday picture in the quantum theory, and there these lines of flux become very discrete and separate, and he was trying to formulate everything in terms of a basic entity, which is the line of force. And that object is like a string instead of a particle. And then he was saying these strings will move about and interact with one another according to quantum laws. So that was the picture he was actually trying a lot to make precise, but he didn't succeed because, again, with electromagnetism, it's still very difficult, even in the quantum theory, because of the reason I mentioned earlier that the quantum effects are actually very small in electromagnetism. The fine structure constant is very small. But as I will now try to tell you, Dirac's idea was very far-seeing because it is not quite in quantum electrodynamics, but in the strong interactions in QCD that this idea is essentially realized. And that's where the strings, I would like to say, very naturally appears. So that's what I'm going to now try to tell you. These strongly interacting Yang-Mills quantum field theories, like those of QCD, are very different from those of quantum electrodynamics. And in fact, they are very difficult to solve using the same techniques, what is called perturbation theory. Those techniques don't really work for Yang-Mills theories. And the underlying reason is that the strength, the corresponding fine structure constant, the analog of the fine structure constant, is of order 1. Unlike the 1/137 that was there for electromagnetism, in the strong interactions, precisely because they are strong, they are of order 1. And that's where that's why the field picture becomes more difficult at the quantum level to work with, because you have to really use the whole machinery of quantum field theory. The classical description is not a good approximation at all. This is why you don't see these forces at the classical level, the strong interactions or even the weak interactions for that matter. But now there is an opportunity, because maybe the quantum field theory description in terms of these Yang-Mills theories may be difficult because these interactions are very strong, but maybe that may make the lines of flux picture more useful. Maybe that is, and we saw there that there is potentially a flux tube. So now maybe can we find equations for the motion of these strings like Dirac was suggesting? Is that maybe possible? And in fact, people tried to do that. They looked at a quark and an anti-quark. The Q bar is like the antiparticle of the Q. And they could try to model various bound states of these quark and anti-quark in QCD. And they seem to be, and actually even now, if you see that in the data book, the particle data book, the pattern of the bound states of these mesons are very close to the excitations of a relativistic string, like the harmonics of a string, the same string of this flux tube. But there were other things that were not quite agreeing. And so this simple string picture of just a free string moving in the four-dimensional space-time, that captured some aspects, but not many others. And this is why people were not sure what to make of this string-like description, because they didn't have equations for these strings, for the dynamics of the strings. And that is what is now beginning to change. And this is because, and people now understand why, because you saw in that picture that I had drawn, or in that movie that I was playing, that string-like object happened to be like a fat string. It was like not the kind of thin strings that you might visualize, like a thin rubber band or a thin thread. This has thickness, really a fat thickness. So this is why it is fairly rigid. I mean, it's like you could see it was quite rigid. It was more or less like an elastic rod, but it had this thickness. So that makes it difficult to model it by in terms of a thin string, at least in four-dimensional space-time. So that's why the detailed properties were very different from those of these thin string-like objects. And that's one of the things that really had stumped people. But in the last 25 years, one of the big advances in our understanding has been that that at least for many of these Yang-Mills theories, close cousins of QCD, there are equations for these strings. And the surprising thing is that these equations are really equations of motion of a string in a higher dimensional curved space-time. So that's maybe a lot of things to unpack over there. And this picture will maybe help a bit. So the picture at the moment, just take it as a picture that imagine our world is a four-dimensional space-time, that our world that we know is a four-dimensional space-time which is sitting on the boundary of a five-dimensional, higher dimensional space-time. And in fact, it's very easy to find these higher dimensional space-times of which flat space-time like ours can be a boundary. These are called anti-de space-times or ADS space-times for short. And they arose first in the theory of general relativity of Einstein, and I will come to that. So these curved space-times are things that people had studied earlier. So the remarkable claim is that if you think of a thin idealized string in the higher dimension, when you try to describe its motion in 4 dimensions, remember the 4-dimensional space-time is only some kind of a hologram, some kind of a boundary or a screen for this higher dimensional space-time. In such cases, you can imagine like you only see a shadow of this higher dimensional string, and that shadow can be much thicker than the original one. You may have always seen this phenomenon that if you shine a torch on a wall and you have some object, the object appears much more blurred and fuzzy when you when you look at its shadow on the wall. This is a bit like that. So you should think of our 4-dimensional space-time as some kind of a boundary screen or a hologram, as it's sometimes called, for a higher dimensional space-time. So the insight was that that you can describe the equations of strings like in the strong interactions through going to a higher dimensional space-time. So this brings me to, so I brought in curved space-time, which I had mentioned right at the beginning of the talk in the context of Einstein's theory of general relativity for describing gravity as curved space-time. And now I seem to have brought in this curved space-time again in the context of the strong interactions. So let's try to unpack that a little bit. So now let me bring in the gravitational force once again back to the stage after we had left it right in the first slide. So Einstein's equations for these curved space-time are also a generalization of Maxwell's equations. That's how Einstein wrote these equations that you see in this picture as a generalization of Maxwell's equations, which describe the geometry of space-time in terms of something called a metric field. They are, but they are also differential equations, so they are classical. It was a purely classical description in 1915 before quantum mechanics was fully developed. But people therefore had tried to understand what is the quantum description of gravity. And there they found that when you try to quantize the metric field, just like people tried to quantize the electric field or the magnetic field that I just mentioned earlier, but when people tried to quantize the metric field, you would think the field which gives rise to gravitons as opposed to photons, it didn't really work. There were some kind of infinities you couldn't really make sense of. The usual quantum field theory framework does not seem to work. And this is where, again, almost like by accident, people realized that, in fact, by studying the string description for QCD, they realized that among the excitations of a relativistic string is the graviton. And And when you consider the interactions of the graviton as part of the string, then its interactions are perfectly finite. All these infinities are no longer there. And people developed a well-defined set of rules for the interaction of these strings, which generalize the so-called Feynman diagrams of which people used to study quantum field theory. So there, people tried to represent the space-time trajectory. So you see time here and space here by one-dimensional lines. So this is the world line of, say, an electron, positron. This is the world line of a photon, and another pair here, and these are interacting with each other. So if you wish, an electron and a positron are interacting with each other by exchange of a photon. This is the Feynman's very pictorial way of visualizing these interactions of in quantum electrodynamics. But people realized you can generalize that to in trying to understand the interactions of strings. By now, instead of a world line, you think of a world sheet, a two-dimensional surface. So just like a particle moving in time traces a one-dimensional line or a world line, a one-dimensional string, and here I've drawn a rubber band-like closed string, when it traces its history in time, it traces a two-dimensional trajectory, a two-dimensional surface or a world sheet. And these descriptions, so you can talk about the interactions of these strings, and things turn out to be well behaved. And this seemed like giving a right framework for a quantum theory of gravity. So you see, what I have told you so far, just to make sure I haven't lost you, what I tried to tell you was how string-like objects very naturally arise in both the Yang-Mills theories, like in the strong interactions, which in itself owes its origin to the electromagnetic interaction. And we saw how string-like objects from these lines of flux will appear. But now I'm telling you that they also appear in Einstein's theory to describe curved space-time. There also string-like objects appear. And in fact, the equations for these strings seem to be related. And so the same framework captures both kinds of strings, the strings to describe the flux tubes or the lines of flux of Yang-Mills-like theories, and the strings that describe gravity-like gravitational forces at the quantum level. So they seem to be the same thing, and this is the central insight of this ADS-CFT correspondence and this picture that I drew a few slides ago, that the equations, so let me just revisit what I said then, that the equations governing these Faraday-like flux tubes in a cousin, at least in variants of four-dimensional, this is 4D is four-dimensional Yang-Mills theory. These are the string equations for strings moving in a five-dimensional curved space-time, and those equations in some special limits actually just become Einstein's equations. So there's a remarkable relation between quantum field theories like those of Yang-Mills or Maxwell and its generalization Yang-Mills, and the strings that describe Einstein's equations. But it's a this connection happens very remarkably because, as I said, you're describing the space-time, you're describing the strings by one higher dimensional space-time. This is what I think, maybe just to show that picture again, this is one higher dimensional. So I've represented the four dimensions here. And then there's one higher dimension, which is the space-time. So the remarkable thing I'm saying is that if you want to describe Yang-Mills theory in this four dimensions, you can describe these Faraday-like flux tube by equations for a string moving in this one higher dimensional space-time. And this string strings are very closely related to Maxwell's the Einstein's equations in some limit. So this is what I was saying over here, and vice versa. You can now describe quantum space-time, at least in these space-times like anti-de Sitter space-time, in terms of quantum field theory in one lower dimension, and this explains many puzzles about gravity, like the so-called entropy, the Bekenstein-Hawking entropy of black holes. But that's another story, and I will not go into that at all right now. But just to kind of conclude, let me just say that this picture I was trying to describe is still work in progress. And in fact, there seems to be very fascinating connections of this idea of holography, that the quantum field theory in d dimensions, d space-time dimensions, can capture gravity, quantum gravity in d+1 dimensions, and it has to, that's this idea of holography, and it seems to somehow suggest that at the quantum level, space-time can be thought of as sort of emergent from a more microscopic description, which in a sense has fewer degrees of freedom. And many ideas of quantum information are coming into this dictionary. For instance, about the entanglement between quantum states. Maybe that seems to have a role in determining the geometry of space-time. And in some ways, maybe Einstein's equations are capturing the flow of quantum information in some limit. So these are very fascinating questions which are currently at the forefront of research. And it is all, so it is in fact bringing together things from quantum information and computing, another whole new fascinating area. So what I want to leave you with is the sense that the string-like description comes about very naturally in quantum field theories, and it comes about very naturally in gravity. Moreover, they are related, and through this remarkable holographic connection that is somehow in a way captured over here, that this is the hologram which is somehow capturing the information about the quantum space-time geometry and the quantum gravity in this space-time. And the way this happens, as I said, is through through very interesting ideas of quantum information, probably, which are currently being studied. So it's a fascinating topic, and I'm sure some of you will probably go ahead and explore this. But let me conclude here by just summarizing. So the idea of strings is not at all unnatural, and in fact has a long history going back to the flux lines of Maxwell and Faraday. And it in many ways behaves as a very an alternative to the usual field description. This is not so pronounced for Maxwell and Faraday for electromagnetism, but it is becomes more pronounced and more important when we consider the Yang-Mills theories that describe the strong interactions, etc., which are highly quantum theories. And here the string-like description seems to be in a way easier to deal with than the field theory description, but it's very subtle because the equations for these strings appear to be higher dimensional equations, and therefore it connects this idea of these strings to that describing gravity in that higher dimensional space-time. And as I said, it hints at a somewhat unusual picture that at the quantum level, if you want to understand space-time at its fundamental quantum level, that we have to think in terms of an alternative description, which is a kind of a holographic description from which, due to ideas from quantum information and entanglement, the space-time itself emerges. So that's all, and thank you very much for your attention. I'm happy to take questions.
Yes, thank you, Professor, for this captivating talk. I'll say you started from Maxwell's equation and then ended up to the string theory. Time to take questions now. People can raise hand and then question.
So there is some question by, I think I see on Kshitij. This says, "If you so then why haven't we proved it through experiments?" Yes, very good question. We, we are trying to do it experimentally, but you should realize that some of these effects are still very small. The quantum effects of gravity show up in a very small length scale. That is the simplest kind of measurable effects which show up at very small length scales. And those are difficult to access experimentally. It's like gravitational waves themselves. They were a prediction of Einstein's equations, but no one thought that they could be observed because they are so tiny. But it's a remarkable technological feat that 100 years afterwards, we have been able to, 100 years after Einstein, we were able to detect gravitational waves, even though the kind of, it's sheer ingenuity. Einstein himself thought that no one will ever discover gravitational waves. So I think it is a function of the technology we have and how we understand it. So I'm very positive and optimistic that we will find these ideas will give new kinds of experimental tests, especially if we understand the relation to quantum information, to strongly interacting systems. There will be some signatures which will be very stringy. I should also say that when people study on numerically, they simulate the strong interactions on the lattice. And the movie that I showed was a picture of such a simulation. You really see those string-like objects. So at least in numerical experiments, you can actually see those. It's more difficult, I think, to experimentally see them, though the spectrum of the mesons is kind of consistent with strings. But I think for QCD itself, if we understand the exact equations for the strings, we will be able to test in QCD, in the strong interactions, in the properties of the strong interactions, we'll be able to, I think, test more properties of the string-like description. But for that, we have to develop the string description for QCD. I mentioned for cousins of QCD or Yang-Mills-like theories where we have now some control, but I think a lot of effort is going into trying to understand how we can generalize that to other theories, to QCD and other things. So I'm quite confident that we will, through all these things, we will, and with developing technology, we will be able to experimentally measure it maybe in your generation.
Yeah, hi. My name is Ganesh.
Hello.
Hi. Thank you for a very wonderful description for people like me who don't normally understand these things very easily. I have some simple questions. I hope you will be able to
Sure.
sort of So, this compulsion for going for higher dimensions, when you go from regular quantum gravity to string, compulsions are mostly mathematical singularities. That's what you're saying, right?
Actually, for the remarkable thing is that in the case of these field theories, it is almost forced upon you. Even if you study Yang-Mills equations in 4 dimensions, it is almost forced on you if you want to describe the string-like objects. The way to describe them is in terms of this higher dimensional string. So the equations of motion are
Your voice is breaking, unfortunately. I'm sorry. Yeah.
sorry about that. No, I was saying that it's mathematically almost forced upon you that even for describing Yang-Mills theory in 4 dimensions, you need to talk in terms of a string in a higher dimension. It's almost that it's not a matter of choice. Even what I want to say is that that's the natural description. And I think we should be open to that, and will be able to see signatures of that, because that, at least in these QCD and strong interactions that we have, that extra dimension has a natural interpretation also in terms of sort of the energy scales at which you're probing the system. So it has a natural meaning, this extra dimension.
So one more question related to that is that if I consider, for example, Young-Mill-like field theories as a zeroth order calculation on some parameters, uh, is it possible to make predictions which are around Young-Mills like, which has string effects coming in as perturbatively, and then make an experimental proposal for bringing that in?
I think it should be possible. At the moment, we have, I think the best understood cases are for, as I said, dozens of units. With extra fields and extra matter. But if we understand from UCD, I think we will be able to describe some detailed features of the strong interactions. As you probably know, in the nuclear force in the strong interaction, there's a plethora of particles, mesons, baryons, hadrons, whatever, and they all have, seems like a zoo of a lot of particles, and it's very difficult in using the Young-Mills field-like description to make sense of all these particles. I think the string-like description will organize our understanding of the hadrons and all these particles, their decays, their interactions with each other. I think it will organize it and lend itself to experimental tests. So in response to the previous question, this was what I was alluding to.
Thank you. I have a few other questions, but I think I'll let others speak. Thank you.
Thank you.
So next is Harak. Harak, you can unmute yourself.
Hello, sir. I'm Harak, and it's actually very fascinating and fantastic to listen to such a topic with you. So, and actually, I have many questions on it. So, basic question is that, as we all know, that how electromagnetism arrives, that if we are constructing a local phase invariant in gauge theory, or with what we can say point-like particle system. So it's not actually local phase invariant, and to make it local phase invariant, we have to add certain terms that we ought to call it as a vector potential. And so how it photon come into the existence of quantum field theory.
Correct.
So, what about the string theory? Like, is it local phase invariant or is it gauge invariant? And if it is, then what kind of particle it suggests, what like photon and all? What kind of gauge boson or a scalar boson it suggests?
So, yeah, string theory has a lot of this sort of gauge invariance in it. To make the description simple, it has a sort of the simplest description has a lot of built-in redundancy through this gauge invariance, and that leads to actually not only Young-Mills like bosons or electromagnetic bosons in the simplest case, but also the graviton and its gauge invariance. The gauge invariance of gravity is diffeomorphism invariance, or the ability to change coordinates. So that invariance under change of coordinates, or general covariance as it's sometimes also called, that gauge invariance is also built into string theory, together with many other more exotic generalizations of that gauge invariance. So it's actually a much more complicated gauge invariance system than most of the field theories we are acquainted with. But it includes all the gauge invariances that you are familiar with. It has those and more.
And yes, sir. Another question is that in point-like particle, we are describing Dirac spinors to have a spin of it. But in string theory, how can we describe a spin system? Is it kind of Dirac spinor or something else which can associate it with a spin?
You can describe a Dirac spinor in string theory. You can describe particles of spin half, spin 0, spin 1, spin 2, even spin 3 half. There are and the spin half particles are the usual Dirac spinners. So they are all they all arise as excitations of string.
Okay, so I have just one question, last question. That as you can say that this is a sheet type interaction. It's not a point-like interaction which is suggested by Feynman. It's a two-dimensional sheet which is interacting.
Correct.
So in quantum electrodynamics, processes are spontaneous. What we are calling it vortices of it. But what about string theory? Because it's a sheet-like system, then is it spontaneous interaction in vortex of any interacting charge or charge particle, whether any field?
You mean spontaneous in the sense of
interaction? Spontaneous in terms of interaction, like as the Feynman diagram suggested.
Like some spontaneous emission or something, like you're saying?
Yes. Because as we can focus on the vortex of the Feynman diagram, it suggests spontaneous emission of photon as well as absorption. But string is a two-dimensional state. So how can it possible?
It's not point-like, and that is important because the point-like description in quantum field theory is very problematic because it gives rise to a lot of the infinities of quantum field theory precisely come from that point-like vertex-like interaction. You could kind of shove it under the rug, or you could kind of deal with it in some ways through this process of renormalization. But it is actually, in some ways, even in quantum field theory, you should really think of that vertex as smeared out in the quantum level, and you think of a kind of a dressed electron with all kinds of virtual particles around it, and that vertex is really not quite a point-like vertex, even in quantum field theory. At least in the quantum field theories you can make sense of. String theory just takes that to a further extent, and now instead of a vertex, but you still have an emission. What you actually measure are the particles far away. You are never really looking at the point-like interaction. All you measure is that some photon was spontaneously emitted by an electron, and you measure that photon in your detector. But that same process happens even with a string, except now you don't think of it as a point-like process, but one string has split into two strings, and you measure those strings far away. So to all good approximations, it will behave like quantum field theory, but at the very small scales, it removes some of the problems of quantum field theory.
Okay, sir. Thank you very much, sir.
Right. So I see no more hand raised, but there are questions in the chat box.
Yeah, there are many questions. I'll just try to take a few of them. So the particles, someone has asked, is particles in a string, interaction between them is considered a string or both? Yeah, well, I would say that the particles are excitations of the string, are modes of excitations of the string. Just like when you stretch a sitar string and pluck it, you get one mode, or you pluck it in a different way, you get another mode. And these are, so in a case of a string, you get different particles by plucking the string in different ways. So that's, I think, what I would say for that. How do we know that the lines of flux bundled up into a string-like tube and not thin between quark and ion? So one of the ways to know that is from numerical simulations. The ones that I showed you, you know that there is a thickness, and there is a length scale in QCD, which is set by the strong interactions. And there's many direct and indirect evidence that that thickness of that flux tube is set by the length scale of QCD. So you can, another way to say it is that even in superconductors, you can experimentally measure similar things, that those flux tubes have a certain diameter. And there's a similar reason for understanding the diameter of these flux tubes in QCD. So, and besides numerically, when you simulate, you see the picture, the movie I showed you was an actual numerical simulation. These are very complex simulations. They are not just an animation. It's actually made of simulating the underlying equations. So another question is about how virtual photons may have mass. I don't know if it's correct. If they have mass, can they travel at the speed of light, etc. Yeah, I mean, a virtual photon is not a real. I mean, it's by definition not a real photon. So the idea of it having a mass is not a very meaningful concept. It is only the real particles that you can measure that you can attribute a mass. I mean, a real idea of a mass. So the virtual photons, it's virtual, so you can say it's that the so they're not real, and therefore the energy square may not be equal to p square. But that doesn't mean that it has a mass. So I think it's a little misleading to say it has a mass. But all the interactions, virtual, real, all the interactions in QED are limited by the speed of light. And Higgs boson resists mass, Higgs boson interaction resists mass to go at the speed of light. The Higgs boson is a massive field, and it is definitely it creates masses for many of the particles, and therefore makes them travel at less than the speed of light. Another question is about the alpha values, approximately 1/137. Is this the fine structure constant from the Bohr atomic model? Absolutely, exactly that. This is the same object that comes in the Bohr atomic model, because there also you have a plus charge and a minus charge which are interacting with each other, and the strength of interaction is proportional to the square, and the dimensionless object that that kind of governs everything is the fine structure constant. So so it's exactly that. Why is it necessary to have 5 dimensions to explore Einstein theory at the quantum level? Well, I mean, actually, in some ways, strings seem to require, in some ways, additional dimensions for their equations of motion to be consistent at the quantum level. So there is otherwise there. So it seems as if we may need to. I mean, the simplest ways to describe strings in consistent equations for the strings at the quantum level seems to require additional dimensions. It is not by choice. It is something that you need to have for the consistency of the theory. Someone asking whether it's everything is just a kind of vibration. Yeah, maybe we have to see. Well, as I said, string theory hopefully will be able to confront with experiments, but in some ways, if you believe in the general picture, you can perhaps think of many of the particles as different vibrational modes. But I should stress that we don't, until we still have the complete picture, it's only a provisional understanding. Yeah, so about time, I think string theory doesn't add to anything more than what in general relativity and special relativity you learn about time. I think, except maybe, yeah, I mean, space-time we think is emergent, so time perhaps is also emergent, but we don't really understand that very well. So the role of time at the quantum level is something we are not, we still don't have a good understanding of. About computational approaches, people use computational approaches for many aspects of string theory to understand the different solutions of the equations. There are, in some sense, many possible solutions, and which are the solutions that are likely to which are the ones that are likely to describe our real world and so on. I think it's a computational problem. about an atom in string theory, well, it doesn't look very different. I mean, at that level of coarseness, the atom is very much can be described in terms of electrons and protons, which are amongst the particles presumably that arise in string theory. So at least at the atomic level, it's not very much different, because any way to discern the stringy nature would be at a much smaller length scale. So about the quantum wave function. So when we talk about the quantum mechanics, quantum space-time is emergent. Yes, you can say that. Yeah, you can say that many in fluid dynamics is an example through which many sort of underlying atomic descriptions give rise to a continuous description of fluids that you describe by Navier-Stokes equation. And you can really, so in some ways, the continuous description of Einstein for space-time is perhaps only like a fluid dynamical description. It's a coarse-grained continuum description of something underlying which is discrete. And the holographic projection to lower dimension, in some sense, there's no source that is projecting. That's maybe one of the misleading aspects of this terminology. It's not really it is just that in some ways you can think of all the information is captured on the boundary of that. The information, the same information is encoded in the boundary of the space-time. The information in the higher dimensional space-time, the gravitational theory in the higher dimension is encoded in the one lower dimension. So it's not a projection. And finally, about quantum space-time, Einstein space-time. Well, Einstein space-time is, like I said a little while ago, it's a more continuous description, while quantum space-time, the space and time is itself likely to come about as a approximate or coarse-grained description, which is discrete. So yeah. QCD is successful because, you mean QED is successful because of the strength, the strong interactions is small. So that's why a QCD is difficult to describe using techniques of strong interactions, because techniques that apply to QED, because the strength of the interactions is large, of order 1. So QCD is difficult to describe. That a strong interaction, the analog of the fine structure constant, is of order 1. So that's why, so in nature we have QED where you can describe with a small number, and QED with a larger number. So those are two different theories, and this is why QCD, the string-like description, is maybe more compelling, more pronounced, as I was saying. Whereas in QED, you can get away with the usual description in terms of quantum field. About books for further study, I think anyone who's interested in this should study quantum field theory first. Quantum field theory you can study from many books, introductory books like Ryder. There's a very nice book by Anthony Z called Quantum Field Theory in a Nutshell. And there's a new book by him also, which is sort of the bare bones quantum field theory in some sense. And there are even string theory. There's a book which is available in an Indian edition by Barton Zwiebach called First Course in String Theory. So you can look at any of these. Yeah, the James Webb Telescope. Yes, we hope not only from the James Webb Telescope, but other telescopes which are probing right to some of the things at the Big Bang. We might be able to describe. Maybe some of the experiments might tell us more about string theory. About the PPT, I can share it with Gurudutt, and yeah.
Yeah.
My question is, what gives a perfect description of reality? It's, I think, philosophical question. Is it the point-like field theory or string theory? Because experimentally, we can see that point-like field theory is extremely good, suggesting fundamentally very well-defined particle and standard model. And theoretically, string theory gives very well description of graviton as well, some another particle. So which gives perfect description of reality.
Physics, I think the difference between physics and philosophy is that physics tries to understand reality through successive approximations, and philosophy tries to just posit something and make some verbal arguments about it. Whereas I think the strength of physics is that through better and better mathematical approximations, we increase our domain of description to better and better, bigger and bigger spheres. And so just because we have a theory which is successful in a certain domain doesn't mean that that's the final word. Otherwise, after Newton's theory was good enough to describe almost everything in the solar system, we wouldn't be looking further, right? Because that was how we could know up till there. So it's not a question to be decided by philosophy. It is a question to be described by our greater understanding of nature. And quantum field theory is definitely very good for all the things that we've described so far. But we believe there's good reason that it will not be a good description beyond what we have discovered so far. And that's why we are aiming to have a more comprehensive description. Each layer of description reduces to the previous layer of description in the appropriate limit. So when Einstein's theory reduces to Newton's theory, or string theory reduces to Einstein's theory in the appropriate limits. So you can only increase your domain of description by this. And that's what physics has always tried to do, increase that through better and better this thing. I don't think physics would like to claim that there is a view of reality, or that is a question that can be settled by philosophical pure thought.
Lots of curiosity as far as the string theory is concerned. It's good to see all the enthusiastic people in the team, but we cannot take all the questions. Let us thank Professor Gopakumar again for taking time to give this wonderful talk and question answer session.
All the best to everyone, and hope some of you will pursue these questions.
Sure, sir. Thank you so much.